Chapter 10, Lesson 6. This will be the final lesson in this chapter, and here we will talk about some concepts related to gases. The first two concepts are effusion and diffusion. So these really are just two definitions, and then we'll take up some mathematical treatments of effusion and diffusion. Effusion is simply the escaping of a gas through a small hole. The reason why balloons eventually get deflated on their own is because the balloon surface actually has little tiny pores through which gas particles can escape in the random movement. So as gas particles are constantly randomly moving around the balloon or the container, once in a while they'll escape. And diffusion is actually very similar, and this is simply the spreading of one gas through a space occupied by other gases. So this is essentially the mixing. You can think of diffusion in short as the mixing of a gas, or gases, mixing of gases. And this will be the rate, or how fast effusion or diffusion happens will depend on the mass of the gas, as we'll see in a minute. So here it says the rate of effusion of a gas is inversely proportional to the square root of its density or molecular mass. So it's an inverse relationship, but it's not directly, or it's not one-to-one. In other words, if the mass doubles, the effusion does not go down by half, but more like by a quarter. So the general principle here is you got nitrogen gas and helium gas. If you take a look after some time, the helium gas went down quite a bit, where the nitrogen gas went down just a little bit. And this is due to the fact that helium actually is quite a bit lighter. Nitrogen gas has a molar mass of 14.01 grams per mole. Helium gas is 400, just 4 grams per mole, quite a bit more than 3 times lighter, which means that helium will escape much faster through those little pores. And the reason why helium escapes faster is because helium particles travel faster, quite a bit faster, so they're able to find those holes. It's not that the helium molecules are smaller. Recall that we said all gas particles have negligible volume, so we don't care about how small gas particles are. It's actually a matter of how fast they travel and find those little tiny holes. Helium, traveling much faster, will find those holes faster, whereas nitrogen not as fast is the idea. And we're going to apply a mathematical concept to this idea. We're going to define and derive something called Graham's law. Now, Graham's law, the derivation of this Graham's law may be a little confusing, so don't worry too much. That should be a square root. But and then that should be in there. Looks like we have a little trouble here. But here's how it goes. Essentially, what we're defining here is the kinetic energy of gases. And recall that kinetic energy is 1/2 mv squared. This is, again, more from physics. But the kinetic energy, how fast the gas particles move, depend on the mass and the velocity. In this case, v is the velocity. And you notice that we're multiplying the two, which means they are inversely related. But because of this squared factor, they're not inversely related one-to-one. So what we do is we take this and we say, well, the kinetic energy of one gas is equal to the kinetic energy of another gas. This is because they both exist at the same temperature. Recall that we said that temperature really is a measure of the kinetic energy, the average kinetic energy of gas particles. So that's why we're able to make this equation. And then we're going to expand each one, Ke1 and Ke2, into 1/2 mv squared 1, 1/2 mv squared 2. Next, what we're going to do is combine like terms. So I'm actually going to put the m2 down at the bottom here, and the v1 squared down at the bottom here. And that's how we get this next equation. And then to get rid of the squared, we'll actually square root both sides, and square rooting this side the square root actually gets rid of that squared, and we're down to essentially this equation finally. And it looks like we still have a little bit of trouble here. But this essentially says that the ratio of the velocity of one gas to the velocity of another is equal to the ratio of the square root of gas 1 to the square root of gas 2. So this essentially is the equation we're going to apply to this next problem. And the problem goes like this. An unknown gas composed of homonuclear diatomic molecules. Now this term is quite entertaining. Homonuclear, that means the same nuclei, which means essentially you have yourself two of the same atoms fused together or bonded together. This could be Cl2, it could be O2, H2, any of the diatomic molecules. It says that this gas effuses at a rate that is only 0.355 times that of oxygen, so a third as fast as oxygen. And we're asked to calculate the molar mass of this unknown gas. Now, because this gas effuses slower than oxygen does, it means that this gas is heavier than oxygen. Now, it's not 3 times heavier, but it's going to be about 9 times heavier. And we'll see this in a minute here as we go along. So let's go ahead and apply this equation. In fact, let's go ahead and do it that way we have a little more space for our working. So our equation for Graham's law said that the square root of mass 1 over the square root of mass 2 equals, this is inversely related, so they'll be on opposite sides, velocity 2 up here and velocity 1. If we say that oxygen is gas 1, we'll say that oxygen O2 is gas number 1. What we can say then is that the mass of oxygen, of gas 1 in this case, is, from the periodic table, 32.00 grams per mole. We can also say that the velocity of oxygen in this case is 1. And whatever the, if we're measuring liters per minute or liters per second, doesn't really matter. We'll say, how about we say liters per minute or something, or we can even say hour. The units don't really matter because both of the units will cancel out as is written here. The more important thing is that the mass of gas 2 is our unknown, and the velocity of gas 2, it says, is 0.355 times that of oxygen, so 0.355, whatever the units are. We don't really care about the units here. So let's just go ahead and plug these numbers into the equation and we'll see what we come up with. So the square root of 32 over the square root of our unknown, let's get rid of that, let's try that again. Square root of our unknown, we can call it M2 still, equals V2 is 0.355 and V1 is 1. So now there's a few ways we can do this. We can cross multiply and divide to solve for this equation. Hopefully you've seen this in math. So cross multiply this way, so we can say that M2, square root of M2 times 0.355 equals the square root of 32.00. Next, let's solve for the square root of M2, which means we'll have to divide 0.355 over to the other side. So we got square root of M2 is the square root of 3200 divided by 0.355. And then to get rid of the square root, let's go ahead and square this side. Let's also square the right side. And we get ourselves, after all the square rooting has gone, M2 equaling 32.00 divided by 0.355 squared is the idea. So if this is a bit messy, or if this is a bit confusing, slow down and take a look at all the algebraic manipulation that we showed you here. So let's go ahead and just plug the numbers in. Let's go ahead and square. Be careful as you put this in, that way you put it in correctly. 0.355 squared is 0.12603, and 32 divided by that gives us 0.12603, 254 grams. And it seems that we're using 3 sig figs here, so this is justified. So 254 grams per mole. then is our mass of our unknown gas. Now this looks very like it may be iodine, because iodine is about that heavy. So if you take a look at the mass of iodine, it's about 126. Each iodine is about 126, 127, I think 126.9 or so. Since you have two of them, 126.9 gives you roughly 254. So it looks like this is the homonuclear diatomic iodine. And this is how you would apply Graham's law of effusion to a problem. It's very practical. We can actually find an unknown gas, how heavy it is, by comparing it to the effusion rate of a known gas. This is kind of the idea. Okay, last thing we'll talk about is something called real gases. Now, all this time we've been talking about ideal gases, and by ideal gases we mean gases that follow certain rules, and those rules, if you recall, were, for example, that gas particles don't take up any space, that gas particles don't have any attractive forces, that they essentially collide perfectly without losing any energy. And this is true of most gases under moderate conditions. However, if you have extreme conditions like high temperature or low pressure, what happens is these characteristics or these tenets that we talked about fall apart. They actually don't hold. So at the extremes of temperature and pressure, this does not work. So here it says these break down at high pressure and at low temperature. I've got it back, or yeah, high pressure and low temperature, and also low pressure and high temperature for the same thing. So what we can say is that we'll have to adjust the ideal gas law. Remember, our ideal gas law is PV equals nRT, and this gas law is good enough for most cases, but if we take a look at the extremes, this gas law is not perfect. It does not work well. So we're going to correct it, and this new gas law will be called the van der Waals equation, after Mr. van der Waal. And here's what it looks like. Essentially, the PV equals nRT gets adjusted. The P and the V factors get adjusted. So if you take a look, because in real gases the volume does matter, we said in ideal gases volume doesn't matter, because in real gases it does matter, we have to adjust it. The pressure has to be adjusted by a volume factor. And the A in here is actually a constant that's derived for specific gases. So if you're talking about oxygen gas, say your A value is 1.36, you simply plug that in for A, and then N, recall, is moles, and then just solve the equation for that. You do a similar thing to adjust it for volume, because real gases do have attractive forces between them, so the volume of the gas particles becomes important. And what we'll do is you'll take the B, this constant here, say for oxygen gas, plug it in there and just solve the equation. We're not going to do much with this. This isn't very practical. This is just to alert you to the fact that real gases have to be adjusted at the extremes of temperature and pressure. Again, feel free to enjoy this table and this concept, but we're not going to do too much with this as we move along here. Alright, and that should conclude for us Lesson 6 of Chapter 10.